Welcome back. We're continuing our study of logic and its implications on practical problems. Today we're going to look at classical set theory. The natural numbers together with the integers would seem to entail a context in which p is true and not p is true. Remember our previous video where we discussed that context could be thought of as a color of paper, and the statements we write on it would be the sequence that are true in that context. So what's happening here? Line is making a statement that's true on yellow paper, that is natural number paper. And the bottom line is making a statement that's true only on blue paper. That would be the integer paper. So we need to pull back and allow our logic to simplify rules that are true in only some spaces and still combine them together. So think of this as a color booklet where some pages are yellow, some pages are blue. We could still talk about them in the same book. Each one of those color sheets might be thought of as what we know as a set. It's saying that the rules and inferences all apply to the things on that same common color. It's a smaller context than the entire universe. Once we start gathering sets together, one of the tools we need is to describe whether we are on that color of paper, the membership problem. There's a spectrum of possible memberships. There are memberships that speak very well to the computational needs, memberships that speak very well to dirty data, and then there's membership in the middle, classical membership of simply understanding intuitive sense whether it is or is not in the set. Today we're going to focus on that balanced point. It's not too computational and it's not too noisy. Judge things as being true or false, and we leave out all other options. We could use the characteristic function denoted by chi. Chi could take in the data we're exploring, and it could be true or false. We then write a set that describes that property. We would say that A is in the set S. One way to write this set is with this notation. We often write the same properties using curly braces. We put the data here in front, and then we put the test that verifies it's in there. Our notation typically uses a pattern of little letters and big letters. The big letters tend to be the things we call sets, or perhaps types or classes. What I have behind me is what's known as the pullback diagram to classify subsets. And we had an entire video on this. You may want to check it out. The takeaway message is this. Remember how we read this as a flowchart. We can follow our paths in any two directions and get to the same place, but they must agree. So let's see what paths we have. What we have down here are terms of capital set A, and we also pair them with evidence that they belong to that subset. They pass the membership test. So the data we have down in this corner is the term, and it's proof that it belongs to the test. Now, these two maps get our data back out in two different ways. When we go up, we simply throw away the evidence that it belongs to the subset. We return it to the original set A. When we go along here, we throw away A and keep the proof that it belongs to the subset. Now we're in a position to run the test twice. If we take A up here and apply the chi test, it's the same as having gone from here to there. But this being a commutative diagram, it should agree with going that direction. We now see we are forced to assign chi of A to true. So the commutative diagram captures the idea that the elements down here are terms of the larger set A which have a proof that they belong to that subset. What can we do with this observation? We now realize that subsets in this model are completely captured by functions from A into true and false. This is the special choice of having selected a classical set theory. We don't have intermediate values such as waiting for future evidence, and we don't have ambiguities of something that is possibly true but may be false. There are multiple mental models that people use to describe this kind of set. For example, a popular one is to think of a bag full of different elements, like a bag of marbles. Each individual marble is one of the members. Another mental model of a set is a gym. We could think of the gym as having many members. The membership list is the entire set. However, we aren't saying that we've seen every member in the gym at any point in time. Quite often, we describe sets by giving just part of the information, and you're supposed to understand that there's more going on. Let me give you an example. In this first example, I've written down all the values that occur in this set, 1, 2, and 3. In this next one, however, I got lazy in the middle. I don't really want to write out all the numbers from 1 to 100. I permit myself to use a notation like ... to tell you any number in between. There are other ways I could have expressed the same test. Here I've said the same thing. I've said that I want the numbers between 1 and 100. Again, I don't write them all there. This is more like a membership in a gym. I simply am telling you who is on my client list. There is a little bit more subtlety. In this notation, I haven't told us yet whether x is a counting number or it includes things like pi and square root of 2. If we want to be precise and match it to this set, we can come back here and indicate the context in which x is in. Since it's a counting number, we use the capital N for the natural numbers. This notation is trying to explain ways to test whether something is or is not part of our set. And that's the only thing that we do with this type of set theory. Because this is such a precise version of characteristic functions, it leads to various generous counting theorems. We can start to predict how big things are. Let's see some of that. A characteristic function on A has to assign a value of strictly true or false to each one of these numbers, because we're in classical set theory. I'll use boxes which I'll check off if they're true and leave empty if they're false. This selector function has selected the numbers 1, 2, and 4 to be in my subset. A different selector function would choose different values. If I erase that checkbox, I erase the number 2. So how many of these selector functions are there? Well, we have 4 independent boxes. Each one has 2 possible choices, true or false. And so we end up with 2 times 2 times 2 times 2 possible choices. Now, that's 2 to the 4. Notice that number 4 in the exponent also matches the size of our set A. That could be a coincidence, but let's see if it is. Let's try to add or remove some points from A to see if the values change accordingly. I've just removed the value 3 from my original set A. What would I need to remove in terms of the choices? I removed that extra multiple of 2 because there's no longer a choice for that third position. So now there are only 3 2s. I see that the number of functions I could select is now 2 to the 3. If I add a point back in, even if I call it something else, that will affect it by bringing that number back up. The result is this. The number of selector functions in a classical set theory is 2 to the size of the set we start with. So the characteristic functions number as much as 2 to the size of A. This is worth some notation. The size of A is often written with an absolute value sign to indicate that we want a number out of A. The term you'll see in books is cardinality. Suppose I select nothing at all. That has to be an option. Which set is that? Well, there's no longer any numbers in such a set. There may be nobody that qualifies for a particular scholarship. There may be no clients in a particular area. However, leaving 2 braces without anything in the middle can be confusing. It can look like we made a typo instead of an intentional choice. For this reason, we have a special notation for the empty set. It's a Norwegian character. But don't mistake this for 0. Now we see why in our previous video we did not want to write down all possible subsets. That growth is exponential. If the size of A becomes 5, that jumps up to 32. If the size of A is 16, we're already into tens of thousands. And once the size of A has 100 or more points, we're starting to run out of atoms in the universe. There's another important class of subsets that we can count in classical set theory. Let's take a look at the classical one known as n choose k. Suppose that I have a set with values and I want to choose a subset, but that it has to have exactly k different elements. 1, 2, 3, and 4 is my starting example. Suppose that I want to choose just one element. How many ways could I do that? Well, I see the pattern. I'm forced to pick a box, and once I pick a box, I can pick no others. If I pick that one, it's the number 3. I can't add another one because it would have 2 elements. And if I pick fewer than one box, it would have 1 element. So if I want to pick exactly one element, A choose 1, I have exactly 4 choices. Why 4? Because A had 4 choices. So this gives us our first rule. A choose 1 is the size of A, the cardinality of A. What about choosing 2? I see here that I could choose 2 by picking 1 and then picking one I haven't already picked. So I'd start out with the total number of choices that I have for A, followed by 1 less. But there's a catch. What if I had done this in a different order? What if first I had selected 2 and then selected 3? You couldn't tell that they were any different at the end of the selection, so I've overcounted. Because I could choose them in different orders, I should divide the entire number of choices by 2. Stepping back and looking at A, I realized the first one was the same as the size of A divided by 1. Now let's try to choose 3 values without looking at an example. See if our thinking can guide us to the choices. Because we're looking at filling in these boxes with true or false, we would first be able to pick any number we want. After that, we would have to not repeat that number if we wanted to get up to 3 choices. Therefore, we'd have to choose from a list of a minus 1. Once more, we could have double counted. Dividing by 1 is just to fill in the pattern. Dividing by 2 is making sure that if I swap the order, I fix that back. Now I need to pick my third element, but I've already fixed 2 of them, leaves me with the size of a minus 2. Once more, I could have done this whole thing in a different order, which means I could have swapped my first one, my second one, or my third one, so there's 3 equivalent choices. The result is this is the number of choices I have for the size of a, choose 3. If we continue this pattern, we perhaps see where it's going. If I need to choose a fourth, I'll multiply by the size of a minus 3 and divide all that by 4. So here's the pattern. When we want to choose a choose k, we first write down the cardinality of a. I'm choosing to think of the cardinality as a finite number. We'll get into infinite later. When I have n choose k, I have any choice for my first element. Once I've selected that point, I have only n minus 1 choices left, and there's a chance that I could have done this in 2 different ways, so I divide by 2. Once I've selected 2 elements to select a third, I have n minus 2 further choices, again dividing by 3. Continuing this pattern on, I stop when I reach k in the denominator. There's a simple formula for writing this down compactly. If we write n factorial as the product 1 times 2 all the way up to n, then we can see that this is part of the n factorial story, only we've stopped too soon. There's a hidden set of products. If I was to continue on the pattern, I would end up with n factorial in the numerator, but that's not part of my formula, so I should divide by that same quantity. Standing back to observe the pattern, I see that both of those are a formula for n minus k factorial. Therefore, if I combine all of this product together with n minus k factorial, I'll have n factorial on the top. But the consequence is I now need to divide by n minus k factorial on the bottom, and using k factorial for the product that's coming out to here. This is what's known as a closed formula. It means basically that you can write it down. But be cautious. This isn't as good as it looks, because it's hiding a lot of recursion inside of this factorial symbol. It's really just naming the repeated steps. It's not actually achieving any deeper understanding of the number. But how big is it? It may surprise you that this number grows exponentially fast. Let's see why that has to be the case. To get a feel for how binomial coefficients, these n choose k's, grow, let's look at our Hasse diagrams. Remember, this was a way that we could model in visual ways how subsets go. At the top of my Hasse diagram, I have the entire set A. We now have a name for the smallest set in there, the set with nothing in it at all. That's our empty set. Between this, there's quite a lot of room. For example, near the bottom are the sets with just a single element in them. Those are the A choose 1s. And by virtue, A choose 0 is exactly the empty set. Above the sets of size 1 are the sets of size 2, or A choose 2. And so on until we reach A. And so we see that all the subsets have to be adding up all of these binomial numbers. But the total number is 2 to the A. So how many terms are we adding up? Well, we start by counting in 0 and end in n. So there's n plus 1 of these. So on average, the size of binomial coefficient n choose k is 2 to the n over n plus 1. That's a gigantic number. Exponential numbers add digits each time. Adding 1 doesn't move the digit at all. So this n plus 1 can't come close to competing 2 to the n. What we see then is that the number of subsets of any particular size might be small. There's only one empty set, there's only n elements with one element in them, and so forth. But eventually, once we get into the thick middle part, these are huge exponential numbers. Keep this in mind when we come back to counting loops in a program. Loops often grow by binomial coefficients. If you get too many nested loops, that number will be exponential on average, and you'll want to avoid that if you want an efficient program. All of this is grounded on one key assumption. This only makes sense for sets where the selector function, the characteristic function, comes back as true or false. That's locked up in the number 2. Any alteration in the logic which would affect the possible outcomes of our selector functions, our characteristic functions, will alter that number 2 to other numbers. We will have more or less options to choose from. The key thing here is that classical set theory gives us a precise way to count because it simply omits from the logic nuance. It's a great way to make predictions, but perhaps that's not the situation you'll find yourself in. When we look at situations for subsets in other contexts, such as computationally, we might lose that granularity and the counting that goes with it. Be careful not to assume that everybody is using classical logic when using sets. It could affect the outcomes. Until next time. That's how you take care of your chalkboard.